Right there, mates. Welcome to the Curious Decoder, Season 1, Episode 1, where we like to unravel the universe's wildest mysteries, one chat at a time.
You got it.
I'm Alex, your host for this grand adventure.
And I'm Mia.
And today, we're diving headfirst into a realm that's more mind-boggling than a platypus wearing a monocle,
Oh, yeah.
quantum computing.
I'm already lost, mate. Are you sure I'm qualified for this?
Oh, you'll be fine. Just try and keep up.
All right. Well, let's give it a go. It is a bit like trying to explain the rules of cricket to a kangaroo.
Yeah.
It's fascinating, but you just aren't sure if they'll ever truly grasp the concept of a silly mid-off.
Well, let's see if we can do a bit better than that, shall we?
Right?
Imagine this, our brains, they're like the computers we build,
Yeah.
right? Getting more powerful every year,
Right?
but we're hitting a wall, a teeny tiny brick wall made of atoms. We can only make transistors, those little switches, in a computer chip so small.
It's true. It's like we've crammed a whole orchestra into a shoebox.
Oh, I like that.
It's brilliant.
Yeah.
But we need a bigger shoebox.
Yeah.
And a whole new kind of music, because at that atomic level, the universe plays by different rules. It's called quantum physics.
Oh.
And that's where things get really, really wild.
Right, you are. Those electrons, the little blighters that carry electricity, they start doing things that would make a magician blush. They can actually tunnel through barriers like a tiny prison break.
I've never thought about it like that.
It's called quantum tunneling, and it throws a real spanner in the works for our trusty transistors.
So instead of fighting those quantum quirks, what if we could build a computer that dances to their tune? A computer that embraces the weirdness and uses it to its advantage.
I like it.
That's where quantum computing comes in.
Yes. Enter the quantum bit a bit, with a twist or perhaps a wobble.
Yeah, into both.
It's like a bit that could be 0, 1, or do a bit of a quantum limbo and be both at the same time.
Superposition, they call it.
Keshy.
It is. Imagine a coin spinning in the air. It's not heads, it's not tails, it's this blurry mix of possibilities until it finally lands. That's what a qubit is, like a swirling vortex of potential.
And here's where it gets even more bonkers. The power of a qubit doesn't just double with each one. You add, oh no, it explodes exponentially. 4 qubits can hold 16 values at once. 20 qubits, they can juggle 1,000,000 values.
It's like going from counting on your fingers to calculating the trajectory of a rocket to the moon.
Wow.
Suddenly you've got this immense computational power at your fingertips. But there's another quantum trick up our sleeve: entanglement.
Entanglement. 2 qubits linked together like 2 dancers, perfectly mirroring each other's moves no matter how far apart they are. Change one, the other changes instantly. Spooky action at a distance, Einstein called it.
It's as if you had 2 coins spinning on opposite sides of the planet.
Oh, right.
And the moment one lands on heads, instantly that the other one has landed on tails. It's mind-bending stuff. But this entanglement gives quantum computers an edge that classical computers can only dream of.
Right, so we've got these qubits doing their quantum dance. But how do we actually get them to do something useful?
Yeah.
It's not like we can just peek at them and see what values they're holding.
Yeah.
Can we? No, I didn't think so.
That's where things get tricky. To get an answer out of a qubit, we have to measure it. But the act of measuring forces the qubit to choose heads or tails, 0 or 1. And here's the kicker. We can never know for sure what it was before we looked.
It's like those mischievous electrons are playing hide and seek with us. They're whispering secrets in a language we're only just beginning to understand. But even though we can't know everything, we can still use those probabilities, those whispers of possibility, to do some seriously cool things.
We can. And that's where the real power of quantum computing lies. We're learning to harness those whispers to choreograph the quantum dance, to solve problems that would make a classical computer throw in the towel.
Hold on to your hats, folks, because this is where we're heading next. We'll be exploring just what kind of problems these quantum computers can tackle and what that means for the future. But first, fancy a cuppa.
You know me so well, I'd love one. Maybe we can even find a quantum algorithm to brew the perfect cup.
I'm sure we can.
Join us after a brief interlude and we'll delve into the amazing world of quantum applications.
See you in a bit.
Yeah. All right, tea break's over. Back to the quantum realm we go. So we've got these qubits, right? They're doing their superposition tango and whispering secrets through entanglement. But how do we turn those whispers into something useful?
That's the million-dollar question, or perhaps the million-qubit question. It's like having a toolbox full of amazing tools, but no instruction manual.
Hmm.
So how do we actually program these quantum computers?
Well, it turns out that writing quantum software is a whole different ballgame compared to classical programming. We need to learn to think in terms of probabilities and quantum logic, which is where quantum gates come in.
Ah, yes, quantum gates, those mysterious portals that manipulate our qubits like a quantum sheepdog herding those swirling possibilities. But how do they actually work?
Imagine a quantum gate as a special kind of lens that can change the direction and intensity of those quantum whispers. They can flip a qubit's state, create superposition, or even entangle two qubits together.
So they're like tiny quantum choreographers shaping the dance of possibilities.
Mhm.
But can you give us a concrete example of a quantum gate in action?
Absolutely. Let's take the Hadamard gate, for instance. This little gate takes a qubit that's in a definite state, say 0, and transforms it into a superposition, a blurry mix of 0 and 1. It's like giving that coin a good flick so it spins wildly in the air, not settling on heads or tails until we measure it.
Right, so it's not just randomly choosing between 0 and 1, it's actually creating this cloud of probabilities, this quantum soup, right?
Precisely. And by cleverly combining different quantum gates, we can create complex quantum circuits, the building blocks of quantum algorithms. These algorithms are where the true magic happens, allowing us to tackle problems that would bring a classical computer to its knees.
Okay, I'm sensing a bud coming here.
You know me too well. It's important to remember that quantum computers aren't about to replace our trusty laptops and smartphones. They're not a magical solution to every computational problem.
So they're not the ultimate universal machines, then?
Not quite. They excel at specific tasks, particularly those involving the simulation of quantum systems. Think drug discovery materials, science, or even cracking the codes that keep our online world secure.
Speaking of cracking codes, that reminds me of something we touched on earlier. Shor's algorithm. Didn't you say it could potentially break the encryption that protects a lot of our online data?
That's right. Shor's algorithm is a prime example of how quantum computers can tackle problems that are practically impossible for classical computers to solve. It can factor large numbers exponentially faster, which is the key to breaking many encryption algorithms we use today.
Hold on, so if quantum computers become widely available, doesn't that mean all our online secrets are up for grabs? That's a bit concerning, to say the least.
It's a valid concern, and it's something that cryptographers are taking very seriously. But remember, quantum computers can also be used to create new, more secure encryption methods. It's a bit of a quantum arms race, but ultimately it's pushing us towards a more secure digital future.
So it's not all doom and gloom on the cybersecurity front. That's reassuring. But what about those other applications you mentioned? You said something about simulating quantum systems. What does that even mean, and why should we care?
Imagine being able to design new materials from the ground up, atom by atom, understanding exactly how they'll behave before we even synthesize them in the lab. Or picture being able to model the complex interactions of molecules in the human body, leading to personalized medicine tailored to an individual's genetic makeup.
Now that sounds like the future I signed up for. But how does simulating a bunch of atoms on a computer translate into life-saving drugs or revolutionary new materials?
At the heart of it is the fact that quantum computers can speak the language of the quantum world in a way that classical computers simply can't. They can simulate the behavior of electrons, atoms, and molecules with an accuracy that would have been unthinkable just a few years ago.
So we're talking about a revolution in fields like medicine, materials, science, and potentially even our understanding of the universe itself.
That's the potential. But it's important to remember that we're still in the early days of quantum computing. There are still significant technical hurdles to overcome before these applications become reality.
Right, so we're not quite at the point of teleporting ourselves across the galaxy using quantum entanglement just yet. But the possibilities are certainly tantalizing.
Absolutely. And while we wait for those possibilities to unfold, I think it's worth taking a moment to appreciate the sheer intellectual achievement that quantum computing represents. It's a testament to human ingenuity, a demonstration of our ability to understand and manipulate the universe at its most fundamental level.
Well said. And on that note, I think it's time for us to wrap up part 2 of our quantum adventure.
Yeah.
But don't worry, folks, the journey isn't over yet. In our final segment, we'll be exploring some of the broader implications of quantum computing, from its potential impact on society to the philosophical questions it raises about the nature of reality itself.
Stay tuned, Curious Decoders, because things are about to get even more mind-bending.
Right, then Curious Decoder's back for the final leg of our quantum expedition. We've explored the quirky world of qubits, the mind-bending power of quantum algorithms, and glimpsed the potential of this technology to revolutionize everything from medicine to materials science.
But as with any powerful tool, there's always another side to the coin. We've touched on the cybersecurity concerns, But there are broader societal and philosophical implications to consider as we step into this quantum future.
Precisely. It's not just about faster computers. It's about the potential to reshape our world in profound ways, and with that comes a responsibility to consider the ethical implications. One thing that's been swirling in my mind is the potential impact on jobs. If quantum computers can outperform humans in so many areas, what does that mean for the workforce?
It's a valid concern. Some experts predict that quantum computing could lead to significant job displacement in certain sectors. Tasks that currently require human intelligence and expertise could be automated, leading to shifts in the labor market.
So we're talking about a future where robots, or rather quantum computers, might be taking over some of our jobs. Sounds like something out of a sci-fi film,
Yeah.
but it says we need to start preparing for that possibility.
Absolutely. We need to focus on education and retraining programs to equip people with the skills they'll need to thrive in this new landscape. Perhaps we'll see entirely new professions emerge, roles we can't even fathom yet, all thanks to the rise of quantum technology.
It's a brave new world indeed. But beyond the practical implications, quantum computing also throws up some fascinating philosophical conundrums. I mean, if the universe operates on these bizarre quantum principles, does that change our understanding of reality itself?
It certainly challenges our classical intuitions about how the world works. The very notion that a particle can be in multiple states at once, or that two particles can be inextricably linked across vast distances, it forces us to question our assumptions about cause and effect, about the nature of observation, and even about the limits of human knowledge.
It's enough to give you an existential crisis over your morning cuppa.
Yeah.
But on the other hand, isn't there something quite liberating about it? The idea that reality is fundamentally uncertain, that there's always more to discover, more to unravel.
Absolutely. I think quantum computing invites us to embrace the mystery, to acknowledge that the universe is far stranger and more wondrous than we could have ever imagined. It's a reminder that we're part of something much grander than ourselves, something that continues to unfold and surprise us with every new discovery.
Beautifully put. So as we wrap up this deep dive into the quantum realm, what's the key takeaway for our listeners? What should they be pondering as they go about their day?
I think the most important thing is to stay curious. Quantum computing is a rapidly evolving field, and we're only just scratching the surface of its potential. Keep asking questions, keep exploring, and keep challenging your assumptions about what's possible.
And who knows, perhaps one of our listeners will be the one to unlock the next great quantum breakthrough. On that note, we've reached the end of our journey for today. A huge thanks to you for being our brilliant guide through the quantum labyrinth.
The pleasure was all mine. And to all our curious decoders out there, keep those quantum brains firing. Until next time, stay curious and keep exploring the universe's wildest mysteries with us.